Okay, so this week is now, we're focusing on Module 4, which focuses on probability tables and relative risk. So the idea of probability tables and relative risk are essential to understanding the importance and relevance of statistics to really everyday life and what a profound change it is. We are still in the world of descriptive statistics in a certain way, and I say in a certain way because we're still describing categorical data. If we go back to the module 2 on categorical data, we looked at 2x2 tables and looked at risk of survival by like say whether you're upper class or not. So you are exposed to a risk or not, and then you have a particular outcome or not. And we can interpret those 2x2 tables in terms of probabilities. And we'll talk about what a probability is. We'll start from foundational principles. And then we'll talk, if we have time, we'll talk about what a relative risk is. And that's the focus of today is really understanding the concepts, understanding the meanings of the words and what is meant when we talk about probability, what is meant when we talk about relative risk. And I hope this would be encouraging, even though they sound familiar, and we use them in I think, somewhat unfamiliar terms. The concepts themselves do, in fact, make sense. And I think getting a broad history, or even just a rather narrow history of where probability came from is crucial. And we never really get a study of that. But what we're going to do is I'm going to go through and follow through the main concepts in the readings for the Open Intro Stats book. And this is chapter 2, starting on page 76. Now, of course, we're not going to read it. I'm basically going to give you sort of I would say a narration, or perhaps a highlight of the main conceptual parts here. I'm going to skip over some parts by necessity. But I would hope that I don't stray too much from what is really crucial here. And this idea of probability, they call it oops, I need to share my screen, I apologize. I'm going to share my screen now to the course readings. But before we do that, I actually want to get us to what is defined as probability. And this is important because probability actually came from France. And so I'm going to share my screen. I'm going to show you my web browser with the Oxford English Dictionary. I think this is Google Chrome. Let me make sure we have this. So if you don't know, the Oxford English Dictionary is available, of course, through Harvard. Otherwise, it's supremely expensive. Do you see it? You see this little screen here? I don't see any indication that that's there. Let me stop the share and try it again. I don't like this. Hold on. And people may wonder, well, why are we focusing on words? Well, I think someone might have said yes. Oh, you can now. Now you can. You see something that says chance, right? Noun, adjective, right here. I hope. Okay. I hope so. I don't see. I'm sorry. Okay, now you don't. I apologize for these technical difficulties, for lack of a better term. Okay. They will often say, "Don't shoot the messenger," and I would say, just don't shoot wherever these data came from. Now you should see this. You should see a web browser here. Yep, now I see this. Okay, good. Okay, so here we have the word chance. If you look at probability, it's actually related to the term chance. Good, thank you. Thank you for the feedback. Chance actually came out of quite literally risk or games of chance. In fact, that's what you'd say in French. You say you could actually say bon chance, which is like good luck, bon chance. So when we talk about relative risk and we talk about probability, think about chance. And in fact, that's what relative risk, that's what probability is actually talking about. It is actually talking about what is the chance of something. And this is important to understand because it helps, I think, qualify some concerns that some of students have expressed to me about the difficulty of this idea. And it is difficult by definition. Chance is counterintuitive. And it really arose from games of chance, literally the roll of the die. And this is where understanding where the word comes from is extremely important. So if you notice, if you can read this definition here, I'm going to just do a little highlighting. Annotate, I'll do the spotlight. I think I should use the spotlight, yep. Look at the definition here. What is this? Chance is defined primarily as the falling out or happening of events, the way in which things fall out. There's this falling out idea. Well, it's because it's related to the Latin word, I think I might say that, cadentia. And that means to fall. Well, what did that refer to? The falling of dice or the falling of cards. But it's actually, if you look at some of these older references, they actually refer to what is not really explained. It's just what they say in French too, au hasard, or kind of haphazardly, we'd say in English. And the point here is that it's considered, in fact, you can even see in the second definition, it's considered an accident because before about the 1770s, when the idea of chance was brought into existence as a way of explaining phenomena, we had a very mechanistic view of the universe. In other words, it was very deterministic as well, mechanism deterministic. So you would have the French philosopher Descartes, who would say, you know, everything's an automaton, and there's a machine, there's a cause, and for every cause there's an effect, and that's determined. And the famous philosopher Thomas Aquinas thought of God as the prime unmoved mover. So the modern analogy would be, think of our entire world thinking of, or the Western world really, thinking of cause and effect in terms of dominoes falling. And God is pushing that first domino into existence, that's Genesis, and it's falling all the way down. And you could see that in action. You might you might be able to build a lever or a robot, or Descartes talks about this. He talks about some mechanisms that were built in the 1770s that seemed to work. You push a lever, okay, something else would happen. There's an action, there's a reaction. And that mechanistic causal universe seemed to play no role for chance. And when chance came into existence, it was because of games of chance. It was because of people were playing, the French were playing dice and throwing cards, and you knew that by accident you could win, by accident you could not win. But it isn't just chance as being fortuitous. It is now the idea, it wasn't until about 1930 or so that we really came up with the idea of chance as something that could be more formalized and as a principled means of interpreting and forecasting the unknown. So think of chance as not as an exception or an accident to what is otherwise a determined universe. Chance, in fact, is actually a way of thinking about the universe in terms of chance. Now, I know that's counterintuitive because if we think retrospectively, if we think of the past, we might be able to infer causes. And, I got married because I met her at the certain bar or church, and this is what happened. And the future, of course, is unknown. But we use chance as a way to make principled inferences about the future and also about differences or risks, in fact. And this is when we talk about risk. That's why we have this word risk coming in here. It might sound off, but I think that's because it's related to this idea of risk referring to games of chance, a risky game. Well, relative risk, think of it as relative probability, relative chance. And when you think of probabilities, think of those as what's the chance of something. I hope that's informative, and we're going to focus on this more, but the idea of probability is novel, it's counterintuitive, and in some ways it's still controversial. But what it is it's helpful to think of chance as, I keep referring to chance because I think it's a more common sense, commonly used term. But if you think about games of chance, that's really where it came from. And I just want to show you actually a book that kind of exemplifies this. This is actually a book that I'm reading currently by Annie Duke. She is a poker player. She's won a lot. And she says, well, we can't, I don't even know if this is working, but she talks about thinking in bets. And what she says actually is that life is not like a chess game, if to use the metaphor of chess, because chess is often, I've heard people talk to me about how life is a chess match. You have opponents and you play strategically. It's not like that in real life. In real life, because in chess, there is an optimal solution. You know what the goal is, you know who your adversaries are. And when you're apparently a professional poker player, you're always taking bets. And you're always winning or losing. And you can be fooled into thinking that there's some order there because you won. You had what they call a hot hand. And so there are a lot of fallacies around what are called informal fallacies or cognitive biases around chance, because we tend to think, well, I'm winning and therefore this will work, or something bad happened to me, therefore I made a bad decision. Not at all. What she talks about and what statisticians focus on and is the idea that chance is a way of taming the uncertainty in the world. So, and it's in many respects, it's a clear way of thinking about the world. But if you think about its origin from the French as coming from games of chance and as a fundamental change in worldview, then I think it's much more helpful, both in terms of your personal life, but also in terms of making decisions and understanding what concepts mean. And this is the link to machine learning. Statistics and machine learning people come from different disciplines quite often. Machine learning people are often from engineering or computer science schools. And they'll actually use artificial intelligence to, predict what movie you would like based on your past viewing behavior. But what they're doing is they're actually aggregating your past information and then betting that these are the kind of movies that you like. And that's idea of betting on what, say, Netflix movies you like based on, say, the fact that you watched every Game of Thrones, or not Game of Thrones, but I'm not sure if that's even on Netflix, every episode of Gilmore Girls, then they might think, okay, you're also the kind of person who would like this. So you're taking information about what is known and saying something about the unknown and making a bet about it. And that's where we get to this idea of relative risk. Relative risk is and to probability tables. That if we think about the Titanic data set, going back to the Titanic data set, we had those tables, but we didn't use the interpretive framework of probability. And that's because probability it's a way of thinking. It's thinking in bets. And it's thinking in a world in which there's uncertainty, which can be uncomfortable, which can be counterintuitive. I have difficulty thinking about this myself. You could probably think of examples here, but let's go to the reading. I don't want to bloviate on this. We're already 20 minutes in. And I want to focus on this idea on some of the fundamental concepts that are essential to knowing the rules and how we deal with probability in understanding empirical data. So we do, if you read this, it'll say it does talk about formalization. Formalization simply, I think of it as moving from probability as a subjective term. Remember in a lecture we talk about subjective probability, to probability as in statistical science or in statistics. You can have a guess. Oh, what's the probability you're going to go to you're going to do something, as opposed to what's the probability of rolling a 6 on a fair die. And these are all based on assumptions. And if you go through my R tutorials playlist, go to the last one. In fact, I'll post that to the discussion board. And you will see that I spend about an hour, so don't worry about it. But it's also in the code. You'll see some examples with using R code about how you can actually play around with probability within the R environment. And the utility here, I think, is to not really, how do I put it? Not think of everything as a game of chance, but to understand what assumptions you're making when you talk about probability, what assumptions are necessary, and where you can, how can you describe uncertainty using quantifiable terms. And this is why we talk about being in poor health, given what's your poor health given that you're poor, right? We're linking economics to poverty. Well, this idea of probability and relative risk in 2x2 tables is basically ubiquitous in health research. And they'll often talk about exposure and non-exposure to the risk. So probably the most famous example in the latter half of the 20th century would be the Surgeon General's report on cigarette smoking. Does smoking cause cancer? So if you're exposed to cigarette smoking as opposed to not, does that increase your relative risk or your relative probability of getting lung cancer? And interestingly enough, one of the founders of statistics, R.A. Fisher, was a complete denialist. He was a complete skeptic that that smoking caused lung cancer. He was unconvinced. He found other mechanisms. He thought maybe people who had poor genes selected into bad behaviors, right? If I have bad genetics, I'm just genetically a mess. I'm going to select into smoking, and I'm going to select into early death. So he found a causal mechanism, right? But it's a crucial point when we talk about relative risk. We have to be careful about what we know and what we don't know. That really what led to this idea of, or the fact that lung cancer increases your probability smoking increases your probability of lung cancer is through replication, studies from different locations. And that draws on assumptions too. With lung cancer and smoking, it might make sense. But with other social phenomena, it may not make sense, the relative risk. Maybe, for example, there might be some behaviors or actions where your risk exposure is unaffected, either because you're genetically predisposed to that or protected against that. But there's unknown information there. So that's the caveat here. When we talk about probability, there are some assumptions made, and when we talk about relative risk, it's still descriptive in the sense that we're not making any inferences beyond our sample. We're just describing the relative probabilities within our sample. So we're still in the realm of descriptive statistics. We're using the language of probability. Now, one of the biggest assumptions about probability, when we define it, is that one observation, one roll of the dice, or one piece of information, say one patient or one person who smokes, that person's, that piece of information does not tell us anything about what comes next. So that's why we have to do random samples, and we'll talk about that later. But just think about this. You have independent trials. When we flip a coin, we want it to be fair. When we roll the dice, we want that randomness in there. And I say want because statistically, when we go to inferential statistics, we take advantage of randomness to make principled estimates about what is possible. And I say possible because we can never make a definitive truth with science. It's contingent on our assumptions. Okay, so we talk about these independent chances. What is important is with independent trials, this is a technical term, but independent events with this that have the same probability in games of chance. In the long run, you're going to reach the probability, the actual probability of the event. So if you look at this this figure right here, and I believe it was also on the discussion board, you can see that in the long run, as I say, the house wins. As long as the die are not 50-50, right? This is it looks like this is not even a fair die. Oh yeah, it's a die roll, so you have 1 out of 6. So this is 1/6 of the chance. What I want to do is I want to annotate. I just want to illustrate this. The point here is that not only does the idea of probability, or unobserved probability of a trial or of an event, if we don't know, say, how many sides there are on a die, then we think of p hat is the true probability of rolling a 6 on a die. Now, we already know, of course, that the die has 6 sides. But if it had 4 sides or 3 sides, we won't really know until we get to a certain number. Looks like we're really converging. I'd say 100 seems pretty sufficient to know, okay, it's probably a 6-sided die. So the point is, even with unknown information, with partial information, you can make inferences with enough observations. So what's known when you roll a die and you get a 6? And someone asks you, well, what's the probability of getting a die and you roll, say, a blue colored side? And I'm not going to tell you how many sides that die has, the die has, but I'm just going to tell you that each side has a different color. And each roll of the die is independent of another. So it's a fair die, but I'm not going to tell you how many sides there are. Well, you will know in the long run the expected value. This is what we call the expected value of the probability of the die. So you have to have some knowledge. You know that the trials are independent. You have to know what probability is, that it's basically it is a proportion that is bound by 0 and 1, that assuming independent trials will give us information. Now, this is where we get into complications with probability. There's this well-known concept of the gambler's fallacy, which is, let's assume that we're the person who we don't, we're placing this bet about bets, and we're saying, okay, I've rolled the die 10 times. I pretty much know it's, there's a 33, there's a 3-sided die because it's about 0.33 here. Well, that's called that is a problem here, and it shows a couple things. First, it shows uncertainty in our estimates when our sample size is smaller, and that's why you're seeing these jagged. You're seeing a wide range of estimates. But when you go to the casino, it also if one were to go to the casino, it illustrates the problems with probability in everyday life. That when we make decisions on bets that are not principled or based on knowledge of long-run probabilities, we engage in what is often called the gambler's fallacy, which is the idea that random events are somehow linked, or that basically random events are somehow linked. So, we might look back and we would say, okay, wow, if we're right here, for example, we're in our 7th roll. Well, I was in bad luck, but now look, I got a hot streak. And you roll a die 3 more times or 10 times, and maybe you've won some money. Well, you're above, you haven't done enough trials. But that's how people can become addicted to gambling, is they might see associations or think that they have a greater chance than before. And also, it's fun to win. But again, this is why the house always wins. You go to the casino enough times, you take the earnings that you might win, and then in the long run, you're going to lose. And that's a difficult thing to do. And that's why when we talk about, when I reference the Annie Duke, the poker player in her book, she's talking about what I keep referring to as thinking in bets as a principled decision, because we can fool ourselves, both in terms of thinking about our retrospective history and as well as our future. Just today, I was going to give an example, but you might be able to think of examples where maybe people are making assumptions about how unrelated events are related, so that might mean something. Conversely, people might look at the outcome of something and then falsely infer that as a result of the outcome, they must have made a bad decision. So we can actually make connections where they don't actually exist. So one example for this is, think in your past year, what is the best thing that's happened to you? And then think, what is the worst thing that has happened to you? From a probabilistic view, we would want to be careful not to engage in what poker players call resulting, which is the false assumption that the result is proof of a good decision. Just as we can win by accident, we can also lose by accident. So your best decision of the past year may not have had the best outcome. Your worst decision may have had the best outcome. That's chance. Now, what we can do, of course, is if we can increase our chance, we can decrease our chance. And that's where relative risk or relative probability comes in. You may meet a smoker I think Ari Fisher was one, who will say, well, I've smoked my entire life and I'm lived forever. In fact, the person who's lived forever is a French woman named Jean Calmut, and she was a lifelong smoker. And she lived till I think age 133. And she made a bet with the guy I think it was maybe her neighbor or the owner of her apartments. And she was already in her late 80s. And she said, well, when I die, you can have my rents. You can have my apartments. But for now, until I die, you'll have to pay my rent. Well, that guy made one could say, a wise decision with a very improbable event, which is he happened to bet that this woman would, according to actuarial tables, would pass away soon and he could live rent-free. In fact, I think he died before her. So she lived rent-free. And she also smoked. So don't be fooled by those extremes or exceptions. When we talk about relative risk, it can be misleading in some ways because you may have a huge probability increase in risk, but an overall low prevalence. You may have a small relative risk, but it might have dire consequences. Context always matters with probability. So I know that's quite a bit of a disquisition here, but I think we've explained this idea of probability. It's the outcome of an outcome. So if you think about the probability of an outcome, it's in reference to something. It's the proportion of times the outcome would occur if we observed the random process an infinite number of times. Okay, that's not possible, right? So, also, if you're a systems thinker or maybe just a sociologist, or if you've read anything about the butterfly effect, or maybe if you're religious and you think God has an influence, whatever you might believe, you might really want to question this idea of events in the social world being random. You might even want to question whether or not events in the gambling world are not random. Your decision to play another game, your decision to stop. So there are some assumptions there, and we use methods to control for that. Basically, we would control for that or we'd adjust them. But the point is, that's really the heart of it. It is a way of thinking that if we could observe this an infinite number of times, the probability of rolling heads or tails, flipping a heads or tail on a fair coin would be 0.5. That's it. And it's impossible to do. Tell me how many times you can roll it. Good luck. I did talk about the notation, right? It's between 0 and 1. So just keep that in mind. And when we think about probabilities, we think of them as proportions. A proportion is also a percentage. So a two-sided fair coin has a 50% chance of getting a head and 50% chance of getting tails. And in terms of proportions, we describe that as a 0.5 chance of getting heads, 0.5 chance of getting tails. Notice that those two possibilities or outcomes add to 1. So all possible probabilities, probable events for an outcome should add to 1. So I think that's all I want to say. I did talk quite a bit about the law of large numbers, and that's important as we go along. The idea basically that if we think about signal and noise, if you have more information, you reduce the noise, you get better signal. So unfortunately, if you go to a casino and you have to learn by trial and error, that will cost you a lot of money. Fortunately, by taking this class, you won't have to learn by trial and error. You will be able to take a principled guess or estimate based on the rule of probability. And this is what I said earlier, tip, modeling a process as random. It can be helpful to model a process as random, even if it is not truly random. The point here is that sometimes either the probability can be quite low of connection, right? The fact, for example, that, here's what I really want to explain here. There are statistical methods a little bit beyond this course where we can control or partial out what we would consider confounders. So for example, R.A. Fisher was dismissive of cigarette smoking and cancer because he thought people would choose both. There's a common cause confounder. Well, you might be able to partial out some measure of genetics, well, or some proxy of that, genetic fitness test or strength or whatever he would want to call, however he'd want to measure it. And then you partial that out through multiple regression, which we'll talk about later, then you'll still see that partial correlation sticking out, telling us there's a signal there, even though we removed what he thought was a confounder. So you can do that through a principled process. You can also do it through looking at different sites. As long as there's a good reason to believe that you'd still see the phenomenon in those sites. For example, if you look at, I'm trying to think of something that would be more socially located. I'll give you an example. How about, there are some I was thinking about this, there are some gestures that you might say in certain contexts that are okay in some cultures, but really offensive in others. So maybe you might have a hypothesis that, giving say, what is this? Like this sign is very, I'm not doing anything offensive, I think. If you do this, it might mean victory, and it might mean something really cool. In other parts of the world, it might mean something offensive. In fact, in the UK, if you reverse it, it actually means it's kind of an offensive, slightly offensive gesture. There are other ones, of course, you could think of. It's up to you, the researcher, to make that claim that this is negligible. It's something to discount. Now, we do have outcomes that are disjoint or mutually exclusive. We have mutually exclusive, and then we also have mutually inclusive. Now, mutually exclusive means they can't both happen. It cannot be the fact that when I flip a coin, you get both heads and tails. And that means it's also a disjoint probability. Now, on the other hand, there might be joint probabilities. But before I do that, I want to talk about this Idition rule. If you want to know the probability of two outcomes, say flipping heads or tails, you simply, and here we have the or here, you simply add up those probabilities. Well, we have a 0.5 probability of heads, 0.5 probability of tails, heads, tails, that equals 1. So the probability, if you flip a coin, of getting either a heads or a tails is 100%, or 1. It's the entire sample space. That's the other term that we use. We can also think about it in terms of collections or sets, but I'm going to go to this idea that when they are not necessarily disjoint, that you might have an overlap here. And this is where Venn diagrams, I think, can be helpful here as well. As you can see, you might have face cards and you might have diamonds, but they're not mutually exclusive, because there are some face cards that also have diamonds. And then, of course, conversely, we can say the inverse, saying the same statement. There are some diamond cards that have face cards. That's what we call the intersection. So this is where we use this idea of probability of A or B when they are not disjoint events. So we have disjoint probabilities, and we have those that are not disjoint. I know it's an odd phrasing, right? It's the negative of something. You could say, the events are not disjoint because technically this green space is the joint probability. When you say it's the collection right here, the assemblage, the set is not disjoint. You're talking about the probability of this or this. Those are not disjoint. So how do we do that? We have the general addition rule. And the point here is the general addition rule works for both disjoint and for those rule probabilities that are not disjoint. So, and I'm pointing you to these sections, by the way, because I hope you would highlight them or remember them when you make your study cards or your study sheet for the test. You would want to have these handy. That's a good reason we have them in the box. So if we ask you for the probability of A or B, and you infer that they are not disjoints, and even if they're disjoints, you could use it. But let's say they're not disjoint, you're going to take the probability of one plus the probability of the other minus the probability of both. Now, the probability that both events occur for disjoint events is 0. That's why you can actually use this general addition rule. Because if you say, what's the probability of heads or tails? Well, it's heads plus tails plus both heads and tails, and that's impossible. So that's a 0. That's a null value. You get the same answer. Now, this is what a student had asked. This idea of and or is inclusive in statistics, which means that unless we explicitly say, so when we say A or B, we actually say A or B, A, B, or both. It's like an and or. So it's different than what we normally would think of. This is another way of thinking in probability. Would you like to go to, would you like to eat Chinese food or Italian food tonight? Our minds are sort of our mental software is kind of preset to think of that as an exclusive term. But here we're thinking of, or even in survey questions, you might ask, are you poor or not poor? Are you healthy or not healthy? But in statistics, we're actually using that inclusively. So what's the probability of being, of being poor and male? Well, we want to subtract the that or. We'd want to subtract it if those events are disjoint. I think that's all I want to say here, except just remember, I think when you say or, replace in your mind and or. What's the probability of A and or B? Okay. A probability distribution is, they say it's a list of all possible outcomes. They have to be disjoint. In other words, the observations have to be independent. That's the idea in this survey sample. And they're represented as proportions, and they must equal 1. So the probability distribution for a fair side of coin would be 0.5. And we're going to talk about continuous distributions later, but the whole idea of a distribution here is, a probability distribution is actually, it's a way of representing the data. So here we have, say, the probability distribution of 4 different categories. And if you notice in the left-hand side here, you'll see a probability here. This is different than a histogram, which I emphasized last week. This is, I would call this a kind of a bar chart, actually. In fact, histograms are kind of a bar chart. But the main difference you can tell is, see these spaces here? Conventionally, you typically have spaces with bar charts. Now, I know this will be a little confusing, but this is actually a probability distribution because we're seeing, first of all, the word probability to describe it, but also we see a 0 point, and we see this right here. If you see these represented as percentages, you could do that as well. So if you have a categorical data on the x-axis that are represented on the y-axis as either decimal points bounded by 0 and 1, or as a percentage, that's a probability distribution. It's what's more likely, what's less likely. And this gets us closer to this idea of relative risk or relative probability. You might want to ask, okay, now that we know the distribution, what's the relative probability of earning 6 figures or more compared to the rest? Right? You want to know this relative to this group right here. And of course, if you look at the roll of the dice, you'll see something a little more simple because there's the assumption of independent trials. The next concept I want you to remember is this idea of a complement. I almost alluded to it. This whole idea looks more complicated here, but essentially this idea is you have the probability of an event, and you also have the probability of the non-event. So let's just say I know the probability of getting a heads on a coin is 0.5. Mathematically, all this complement rule is saying is that if you take 1 minus our probability event, you will get its complement. And that is the probability of not getting heads. So take 1 minus 0.5. So if it's whatever probability it is, if it's a probability 0.2, what is the complement of probability 0.2, which is a 20% chance? Well, there's an 80% chance of not whatever event we're talking about, not winning the lottery, I suppose. So the complement, by the way, just to clarify conceptually, doesn't tell us as much as we might always want, because the complement, we're not sure if all it tells us is it's the probability of the event not occurring. It doesn't tell us what those other probabilities could be if we have incomplete information on the entire probability distribution. That's just important to remember, that the complement of an event is not, it tells us the proportion, but it might not tell us exactly what's going on. So to say that you don't have lung cancer because you smoke, that's all it says. It doesn't tell us anything else, because that's not really our research question, right? Our research question, if we early, when we were talking about, say, smoking and lung cancer, it was about what's the relative risk of that outcome. Okay. We spoke about independence of events. The idea of independence is simply knowing something about one roll of the dice or one flip of the coin or one person in your data set or one observation in your sample does not tell you anything about the next observation. Okay? That's all we really want to say. So if you think about the data frame or data sets that you have, think of independence as really a statement about the observations in an applied sense. If we look at the observations in the GSS, we're going to make the heroic assumption that, okay, those observations are independent. So knowing about row 1, that you can read row 1 and know anything about that. tells us nothing about the other. In fact, it would basically say the probability of knowing anything about row 2 in the data set given row 1, the conditional probability is 0. That doesn't always work, but it works with our data set because it's based on what's called the General Social Survey, which is a random sample of Americans. And when you take a random sample, not only can you make inferences to the wider population on a small number of people, which is cost effective, you can also basically, you can make statements such as what we're doing with security or faith, not with faith, but with confidence, that's those observations are going to be independent. Okay. Now we're going to talk about the multiplication rule. So we talked about the probability of some A or B, and now we talk about the general rule. We talk about independence. Now for these independent processes or independent events, we're going to say what's the probability of both A and B, and that's simply the multiplication rule. So, well, here's a good guided practice example. About 9% of people are left-handed. Suppose 2 people are selected at random from the US population. Isn't it reasonable to assume that these people, are independent? Well, what I want to go is, what is the probability that both are left-handed? If you take 2 people, well, you're going to basically, well, first of all, you're going to assume that because you just take 2 people and that doesn't vary, because I am actually left-handed, and I know that to be the case. It's pretty constant. It's a strange phenomenon. It's only increased because of rates of observation. We can safely assume we take 2 people out of the world. We might be wrong. They might both be left-handed, but they each have a 0.09 chance of being left-handed. What's the probability that they both are left-handed? 0.09 times 0.09. What's the probability that they're both right-handed? That's the complement rule. And we can use that here because there are only 2 options. It's like the heads and tails example. So that would be 1 minus the probability of the event. So what we're doing here is we're talking about the independence assumption, which can work if there's a universal probability applied for the whole population, which is true for left-handedness, at least today. And then if that's the case, we can use the multiplication rule to estimate or calculate the probability of 2 events, the joint probability of 2 events. And then we can also get the complement of that probability, as long as that complement is worded correctly. If we say, what is the probability that both are ambidextrous, I don't know what that would even mean. So, because some people might classify left-handedness as being ambidextrous or right-handed, but here we're actually even making an additional assumption, which is the probability of A is right-handed. It means simply that you're not left-handed. There are no ambidextrous people. And that actually happens in practice, so that's safe to say. Oh, look, they even talk about it. It is reasonable to assume the proportion who are ambidextrous is nearly 0. Exactly. I anticipated that because because there are always assumptions to be made. So what I'm trying to do throughout this is emphasize that here we have rules that let us make good decisions that in terms of relative risk and in terms of probability. And those always depend on interpretation and assumptions. I see it's 6 o'clock. I know I can often go longer than is desired, and we're only at page 88 out of, we got to get all the way to 100. So I'm going to take us to this idea of relative risk. Conditional probability is simply the probability of an event given that you know something. So this right here, it's a ratio. So the probability of A given, probability of B given A, that's how you read it, is the probability of both divided by the probability of B. So I'm just highlighting that. And then you have a general multiplication rule, because if we have the or conditional rule, we also have the and conditional rule, which is the multiplication rule. So A and B, what's the probability of A and B? We can think of this actually as a conditional rule as well. The probability of A and B is the conditional probability of B given A times the probability of B. It's just if you notice the word general here, it means it can be applied whether or not those events are independent. I won't go to that, and I also won't go to tree diagrams. You can look at those from the lectures. They're not always that useful for me personally, but if you find them useful, it's a way of splicing these events into different kinds of probabilities, and it's a way of looking at things. There's this concept called Bayes' theorem. We don't really go much into it, but it is informative. Only use the tip that they say I thought was funny. Only use Bayes' theorem when tree diagrams are difficult. Bayes' theorem is for a different time, unless you're interested. It's not what we're going to test you on. We talk about small samples with and without replacement. Without replacement means actually that let's say we have 200 people in a room and we want to take 200 people. We're actually inducing or creating independence when we sample from those 200 people. Because what we're saying is, okay, I draw the first person out of the first ball or whatever out of the jar, and it goes to one person out of the 200 in the room. She leaves, and then we have 159. We do not replace the room with 200 people. That means that we change our probabilities each time we draw people out of that sample. With replacement means you basically, as it says, you sample your students without regard to who you've already picked. So just make sure that that's a careful kind of assumption, that if you can actually have non-independent events, if, I don't know, you do it without replacements. Because, but there are plenty of reasons why you might have non-independence as well. You might have, say, that passengers on the Titanic were I don't know, might have familial relations, right? They came in families. So there might be some grouping there. But don't worry about the simple random samples that we have in the GSS, because that is sampled, it's called a simple random sample, and it is with replacements, technically. I mean, the US is 330 million people. We don't need to worry about that too much as long as we have no regard for who we've already picked. And we have plenty of ways of inducing randomness because it's actually kind of hard to do. But it's smaller if you're doing small samples in psychology, things like that. We can talk about probability distributions as continuous, I want to go to this idea of relative risk. And where was that? I'm sorry, hold on. Go to somewhere around here. This is beyond the course, because we're not going to we're not really going to these other concepts. I thought relative risk was here. Could be wrong. It might only be in the. Let me search for this. If not, I will give you the 5-minute summary of it. I know we're about 10 minutes over. I apologize. Okay, interesting. Yeah, so we have some ideas of risk, but I actually, because we have 2 textbooks in the class, I actually forgot that we don't have it here. And it's in part because it's a very precise epidemiological concept. Remember, risk refers to relative probability, and it is. I'm going to bring up if we can close this window. I'm going to stop the share. If we can close that window, and what I'll do is I'll bring up a new share of the lecture slides. But the idea is, when we talk about relative risk, unfortunately, most of the examples we give seem to show adverse outcomes, but a relative risk can also be a positive relative probability. And it's mostly common in, how do I put it, in social epidemiology or instances where we're talking about risk factors for health. So it is often used in the language of, how do I put it, in the language of health, adverse health outcomes and exposure. So exposure to a health, to some risk factor, and then its consequence. I'm just going to get the lectures here. Are there any questions thus far? If not, we'll continue. And I'm sorry, I'm just getting the lectures here. Where is that? Sorry, I'm actually just looking for the where I put the course lectures. Do I have this? Maybe it's in the archive. Okay, I see it here. Good. All right. There are some important key points about relative risk. It's different than absolute risk. You might have a very high relative risk, but a very low absolute risk. Now, in my view, I think the best way to think about this is perhaps not starting with a 4x4 table, but actually thinking of it in terms of a treatment and control group. So if I can actually open a document here, what I'm going to do is I'm going to try to open a PowerPoint. It seems like my computer is being cumbersome here. Shoot, I apologize. You know what I'll do? I'll just open the PowerPoint here. My PDF player isn't working and I'm doing a force quit, so I'll just open the PowerPoint. Okay. And we'll go to week 4 and I'm open the PowerPoint. All right. So I'm just going to move us quickly to the beyond the rules of probability and this idea that what is relative risk? And we talk about the addition rule and we talk about the multiplication rule for both conditional and disjoint probabilities. When we talk about relative risk, it is a measure of association. I'm not sure if I like the language here, but I'm just going to take you straight to, I think, what is the easiest interpretation. Right here. This is, by the way, slide 117. It's a ratio of conditional probabilities. It's the probability of the event given you're exposed and the probability of the event given that you're not exposed. So I'm sorry, I don't think you actually see this. I didn't share the screen. You should see the screen now. You should see this. You see that? Yep, you see the slides. So you look at slide 117. I think this is the best source of information from the class where you can actually take this and run with it. So here we talk about P as the probability of an event. It's a conditional probability of the event given that it's exposed, or over the probability of the event given that it's not exposed. I'm going to just do a little extra typing here because that's one way to think about it. It might be a little easier if you think about this. Think of an experiment where you have, say, you have one group that's a treatment group, exposure. Let's say we give you aspirin and we want to look at treatment with aspirin. And then you have the second group, and you have 10 people in that sample, randomly assigned. And then you have the control group without aspirin, right? So there's no, they're given nothing. This is the not exposed. And we also have 10 people there. And we track them over time, and we're interested in this well-cited study, you might have heard of this theory that we're testing, that aspirin reduces the risk of heart attacks. So there we have the experiments. We'll start off with a hypothesis. We'll do our experiments. That's what we did. We recruited. I know it's a small n, but it's for illustration. Then we get our results, and it looks like in one we get, looks like we got one out of those 10 people in treatments had heart attack. This is after, say, 10 years. We have a lot of money, but we don't have a large sample size. And in the other group, we have 4 out of 10 in control had heart attack. And we randomly assign these people to the treatment of the control group. It's a random assignment, so we didn't have a choice. Already you can sort of see why we never had an experimental study to see whether lung cancer was associated with smoking. Because it's unethical to do something like this without telling them. You don't deprive someone of life-saving treatments. But what is relative risk here then? It is simply the ratio of one over the other. So what is the relative risk here? Well, it would be 0.1 divided by 0.4. And that would equal 0.25. So what we're saying then is that the relative risk reduction of aspirin, of a heart attack, given aspirin is 0.25%. And that's an important point because if those two groups were the same, let's say we had a 4 in each group, just hypothetically, then we'd have 0.4 divided by 0.4, which equals 1. That would mean there'd be no discernible effect, no relative risk. Notice, by the way, I use an example where we're talking about reducing something. So it's not relative risk, it's relative probability. Now let's assume that we have 8 here in our treatment group. So then we have 0.8 divided by 0.1, which equals 800, by 0.4, which equals 0.200. What does that mean? Well, the key point here, I'm going to actually cut this out for a second so that the text gets a little bit bigger. This here is an increase in relative risk, and we would say the relative risk of for the treatment versus the control, you double the risk of the heart attack given your exposure to the treatments. Here means that there's no effect given the treatments of the outcome. Here, you're saying there's a reduced effect. So there's a bit of an asymmetry, because this number here can go as high as you want, really. You can have a relative risk of an adverse event to be 10, but the lowest that the risk reduction can be is 0. You can't have anything lower than 0. But that's crucial, that relative risk is a ratio of conditional probabilities. But I think it's clear if I give this example, simply because this is actually a conditional probability. If you think about assignment to treatment and control, you're saying, what's the conditional probability of the outcome in one group? What's the conditional probability of the outcome in the other group? And what's that ratio? So I'm telling you now what relative risk entails or tells you. Now I'm going to tell you what it does not give you. Let's go back to what I gave in the first example, which is consistent with what we find in research, which is heart attacks do reduce the prevalence of heart disease. And that might seem good. We can say that it reduces your risk of heart disease by 75% or 0.75, because remember, 1 is an effect of 0. So if you reduce the effect by 0.75, you get a 75% reduction. It doesn't tell us the absolute numbers. Because what really, if you look at the absolute reduction, you can say, well, the absolute reduction is still, it's what is it? The difference. It's the difference between the risk of exposure in each of the two groups. It also doesn't tell you the actual prevalence, the risk prevalence given the outcome. It's because it's a ratio, because it's a relative risk. It's only relative to whatever the baseline is. So what it shows is that you can die of a heart attack without smoking, or you can be like Jean Calment, the longest person living forever who smoked, or who would not die from getting lung cancer. So even though your risk of getting, sorry, not lung cancer, I'm confusing lung cancer with aspirin. The reality is that lung cancer does increase your relative risk greatly, but the absolute risk is fairly low. With aspirin, it's about the same case. So in our toy example, 60% of the people who did not have aspirin didn't die, but one person in our treatment group took aspirin and it didn't help. So friends and family of that person would probably be unlikely to believe that aspirin is actually efficacious. So the point is, aspirin might not have an effect for everybody. Concomitantly, you might not have a truly large effect if the relative group or risk sample is small. And that's true with a lot of statistics. You can't just rely on percentages. You got to look at the raw or absolute numbers. And that's all I need to say. And I know I went over, and I appreciate for those of you who've stayed. And no worries about anything, because we were going to finish up with this. And if you have any other questions, post them to the message board. I know this is counterintuitive, but thank you very much for sticking around. All right, take care.